Hello students, welcome to the course on hydraulics FMH202. So today we are going to start with a new chapter, that is centrifugal pumps. So I believe most of you must have heard what a pump is and what it is used for. So today we are going to study the main function and how it operates. Okay, so that is what we are going to study today. So in the first slide you can see there is an image of a pump. So this section is the pump, and a motor is required to operate a pump. Okay, so this is the motor, electric motor, with it has the mechanism which makes the shaft rotate. Shaft makes the impeller rotate, and when impeller rotates, it exerts a centrifugal force, thereby increasing the pressure energy, and it adds the energy to the fluid, whereby more liquid will be, more liquid will be sucked in, and it will add some energy, and it will lead, it will, when it adds the energy, then you can transport the fluid or the liquid to higher elevation. So that is what pump is used for. So main part of a pump is the pump rotor or the impellers. Okay, this is the suction pipe. Suction pipe means from here the water will be entering or the liquid will be entering, and here this is the delivery pipe where water will be going out of the pump. So with this, let's continue our discussion. So as I've already explained what a pump is, right? It is used to move liquids, gases, or slurries, and it increases the mechanical energy of the fluid. That's why we are able to move the liquid against the gravity as well. And it's a type of rotodynamic pump, in which rotodynamic pump means in which the dynamic pressure is developed by action of centrifugal force. That's why it is known as centrifugal pump. And if you notice that the centrifugal pump works reverse to that of a reaction turbine. Reaction turbine is used to harness the energy of the liquid, but here pump is used to add energy to the liquid. So how the energy is added to the liquid, that's what we're going to study. The main advantage of using centrifugal pumps are it has the high discharge capacity. It can handle varieties of fluid like oil, liquids, and chemicals, sewerage, right? And it has low maintenance. The cost of maintenance is very less, and can operate in high speed without the danger of separation and cavitation. When it operates in high speed, then it can give high discharge. So that is what it means. Okay, so here is an image of a centrifugal pump. So outside this is known as the volute casing. Okay, and in interior of this volute casing there is the impeller. Impeller is the main part of a pump that rotates, and to make this rotate, a pump or a driving some another additional equipment is required to make this rotate, and commonly a motor is used to rotate this impeller. Okay, and with it, impeller rotates, the liquid that is coming from here, this is the inlet point. The liquid that is present here, because it rotates at a high speed, it exerts some centrifugal force, and which is thrown out in this direction, and this volute casing collects the water, and then it goes in the outlet of the pump. Okay, so that's how a pump works. And this is the impeller. It is an image of an impeller. So impellers can be of different types. There's an open type, a semi-open type, and closed means the upper plate and lower plate both are closed. There's a bound two plates are bounded. These vanes are bounded by two plates. This is the closed type, and semi-closed, and the open type. So there are three types of uh, impellers. Okay, and here are the components of a centrifugal pump. So as I explained, impeller is the main part that rotates. Casing, or the volute casing, is the casing of a pump, right, which collects the water and then it lets to the discharge. The shaft is the main rotating element that makes the impeller rotate, and it is connected to the electric motor. Now there are two pipes, suction pipes brings the liquid to the pump, and delivery pipes takes away the liquid from the pump. So that's the only difference. That's the difference between suction pipe and the delivery pipe. Okay, now I will give you a brief how a centrifugal pump works. Okay, first step in any centrifugal pump is the priming. Priming means taking or removing all the air present inside the pump. If there is air present inside the pump, then pump will not function. So first step in operation of a centrifugal pump is priming. In priming, what is done is this suction pipe, the casing, and up to the delivery valve, in the delivery pipe, is filled with the liquid which is to be pumped, and then at that point delivery valve is kept closed. Okay, then the electric motor is rotated. When electric motor rotates, it makes the impeller rotate. When impeller rotates, then it starts to add energy to the fluid, and then finally the valve is open, and this there will be, when valve is open, at the center of the pump there will be pressure will be low, because the water or the liquid that is present there is already thrown out thrown in outward direction, and it is collected in the casing. So the pressure will be low at the center of a pump, and to compensate this lower in pressure, more liquids are drawn from the suction pipe. So this process continues. So that is the operation of a centrifugal pump. And there are different types of impellers or the curve vanes. Okay, there are different vanes. So the orientation of vane can be backward, or it can be radial, or it can be forward. Notice that forward and backwards are more or less same, but the thing is, it depends upon the rotation. Now, if it is rotating in this direction, it becomes backward, but if it was rotating in this direction, the same, it becomes forward. Okay, and some of the property of these different types of vanes are: for backward vanes, with increase in discharge, the head goes on decreasing. So that is a property. For radial vanes or the blades, it is the discharge. With the increase in discharge, the head remains constant. And for forward curve vanes, this forward curve vanes, with the increase in discharge, head also goes on increasing. So they can be employed in different situations depending upon their requirement. So these are the few examples of the different types of vanes. Okay, now let's try to draw the velocity triangles and then do our analysis. So for the backward curve vane, notice that this is the backward curve vane, and this is the impeller. Sorry about that. There's a fluctuation in electricity. Okay, now it's back. So this is the three-dimensional view of impeller, and this is center. Okay, the water will be thrown out, and there outside this there is a casing. Okay, so that is this is the layout of a backward curve vane, and this for forward curve vane. Both backward and forward are basically the same, but it depends upon the rotation. So okay, notice that the inlet velocity triangle for backward and for forward is same. See, it is a radial flow. Okay, there is a radial flow at the inlet section. There is a radial flow at the inlet section. Radial means in radial direction. Okay, radial direction. So at the inlet section for both backward and forward, there is that velocity triangle remains same. The difference is at the outlet point, the outlet of vane. Okay, for backward, the velocity triangle is constructed like this, and for forward, the velocity triangle looks something like this. Okay, if you notice the difference, the VR2 makes the difference. Okay, so in the direction the V2 goes in the direction. Okay, I can say this is towards the direction of the rotation for both the cases. Okay, but the VR2, that is the relative velocity, goes in opposite direction for backward curve vane. So that is the only difference. You need to know this diagrams, okay, to be able to solve the problems. And here VW2 and VF2 are the components of V2. I could have also drawn it here, but I did not draw it here. Okay, so this VW2 and VF2 are the components of V2. Okay, with this, let's go on calculating the work done by a pump. So I have taken an example of backward curve vanes. So I have now made the velocity into two components, that is tangential component VW2, also known as the wheel velocity, and the radial component, or also known as the flow velocity, as VF2. Rest everything remains same. I have also given a force in the tangential direction. So summation of forces in tangential direction is equal to momentum flux going out in tangential direction minus momentum flux that is coming in into the from t direction, considering a controlled volume. So let's me take this as a negative f in, let's say this is negative, so I'm putting this as a negative ft. This sign convention is up to your choice. I normally go by the normal sign convention, that is towards the left it is negative, towards right it is positive. So I'm just following the same sign convention. So minus ft is equal to what is going out, momentum flux. Momentum is mass into velocity, that is rho q is mass times velocity that is going in tangential direction is vw2. So vw2 becomes minus rho q vw2 because the direction is this direction. So minus what is coming in t direction. Since the flow is radial and the radius and the tangents are mutually perpendicular directions, so there will be no wheeling component at the inlet, so there is 0. So ft is equal to rho q vw2. So that is the force. Now work done, we know that work done is force multiplied by the velocity, right? Is work done per second. So force is rho q vw2 times, since there can be two u's, okay, since this w2 corresponds to the outlet, so we have to multiply the tangential velocity at outlet, and we get, this is the expression for work done for a pump that is having a backward vane. So you can similarly you can derive for forward and radial also. With this, let's understand the various heads in a centrifugal pump. So you can see this is the typical layout of a pump. Okay, so there is the sump or the liquid that you want to transfer to a higher elevation, and this is the place where you want to transfer this liquid. Now notice that the elevation difference between this tank, now tank, when I say, I'm considering the full tank point. Okay, so point 0 is the elevation at this point, point 1 is the inlet, point 2 is the in the same line but in the outlet section, and number 3 is the delivery valve, and number 4 is the full reservoir condition. So you notice that the from point or the sum to the pump is the height, the elevation is hs, which is also known as suction lift. Okay, and hd, that is from pump to from the pump to the point where you want to reach your liquid. So that is the delivery lift. So that much height, against this much of height, your pump must work to reach this liquid, the liquid that is present here to here. And overall, a pump must add this much of energy, VW2 U2 over G. This parameter is work done per unit weight of water. So this much amount of head it must add to this liquid for it to reach to this elevation. Okay, so that is the understanding. So let's understand further. So from here I'm drawing the total energy line. Okay, in fact this line should have exactly be touching at this point, but I have kept it a little bit below. That's to show that there is some losses at the entrance and this strainer. Okay, so there will be some losses. To show that, I have kept it slightly below. So as it goes, there will be a negative slope, right? Because as the water moves, there will be some losses. If there was no losses, then this line would be straight. So now this much energy is lost as a frictional loss between point 0 to 1, which is the suction pipe, right? This is the suction pipe, and that much energy is lost at HFS is the frictional loss in suction pipe. Similarly, HP is the hydraulic losses within the pump. Okay, and usually hydraulic losses in the within the pump is expressed in terms of efficiency of our pump. And further, HFD is the frictional losses between pump to the delivery or delivery point or the delivery pipe. This is the frictional loss within the delivery pipe. So what you need to understand is this much energy from this point to this much head must be added additional for this liquid to be moved from this position to this position. So that is the understanding. And new term comes, that is the manometric head. Manometric head is the total head, is the total work done that water needs to be transferred from this point to this point, that is what we have discussed, minus the losses in the pump. So that is what is known as the manometric head. So total head minus the losses in the pump gives us the manometric head. Please try to draw this diagram yourself and practice, because it is important. For now and then I will be referring to this diagram. I will be saying go back to slide 9. You should be knowing where is point 0, you should be knowing where is point 1 and 2 and 3 and 4, and you also should be knowing what is manometric head. You also should be knowing the value VW2U2 over G means. This is the work done per unit weight of water. In other terms, this much energy must be added to this liquid for it to transfer from this point to this point. So that is the basic understanding. Okay, now let's understand the losses in centrifugal pump. So when motor is driven, it has the maximum power, right? The motor is driving the shaft, so shaft will have the maximum power. But all the power that shaft has is not transmitted to impeller, because there is some mechanical losses. Shaft and impeller are connected through some kind of bearings and so many other stuff. So what happens is when it rotates, there is obviously some friction and heat will be generated, and then there will be losses. So this is separated by, this is the difference between shaft power and impeller power, is the mechanical losses in the mechanism. Okay, and further, when impeller rotates, it adds energy to the fluid, but when it does that, there is some losses in the fluid, right, within the pump. So there is some hydraulic losses in the pump. So all the energy that has been possessed by the impeller cannot be transmitted to the liquid, and that is the liquid output power, or that is the energy that has been transmitted to the liquid. Finally, this is the total work done. Now let's talk about the total work done. So we have already discussed there is so many frictional losses. Now delivery or the exit means the final point. Okay, point 4 you can consider. So from the sump to the point 4, or the point 0 to point 4, there's so much of frictional losses and so many other losses. So all the energy the energy that is to be added by the pumps also should compensate the losses. So see, as from the power that is been given by the shaft to the total power that has been added to the fluid, it is there is a drop in energy because there exist so many losses. So with this, let's also discuss about the efficiency. Whenever there is a losses, then it becomes more sense to talk about the efficiency. So let's talk about the efficiency. So like in turbines, there are 4 types of efficiencies in the pump. So let's discuss about there are 4 different types of efficiency. Number 1 is the manometric efficiency, and it is defined as the ratio of manometric head developed by the pump to the head imparted by the impeller to the liquid. In other words, it is the manometric head divided by the total head that is added to the liquid. Now VW2U2 over G is that G over G is going up. That's why this looks in this form, but it is manometric head divided by total head that has been added to the water. So that is the understanding. Okay, volumetric efficiency. Now here what you need to understand is, you really need to go back and understand how the pump works. So whenever the impeller rotates, the water or the liquid that is present at the center of the eye is thrown outwards in the casing, but some portion of liquid again come back to the eye, from some the small gaps and so many other stuffs. From the gaps, let's say, the small amount delta Q again come back to the same eye. So there is a rotation within the pump. So because of this, there is a volumetric efficiency. Okay, so the volume, whatever the liquid that is passing through the impeller is not going through the through the the discharge. It is not discharging from the pump. So that is there. So that gives us the volumetric efficiency. Now mechanical efficiency. Mechanical efficiency is the ratio of power delivered by the impeller to the power supplied to the shaft by the motor. Now you know that motor, shaft and the impeller are connected, and between this there is some mechanical losses, right? Because impeller is also rotating, shaft is also rotating. So the difference between these two energies would be the mechanical losses. And to express mechanical efficiency, so this is the formula for mechanical efficiency. And we know that overall efficiency is the multiplication of mechanical efficiency, volumetric efficiency, and manometric efficiency. In other term, it's the total power, output power from the pump to the total input power from whatever it is driving the pump. So that this is the expression for the overall efficiency. This is the power that is, that is output from the pump, or the total energy that is given out by the pump and total energy given to the pump. So that gives the overall efficiency of the pump and motor combination, that mechanism. This is the overall efficiency of that entire system. Okay, so I will keep it to this point and we will continue in our next lecture. Thank you.